Okay, thanks the organizers for the invitation. It is my pleasure to give an update on the LHC results. And I was given this title called LHC Update, New Results, New Techniques, and New Ideas. Now, the symposium organizer wished for a somewhat different talk than those given at the previous symposia, focusing more on new ideas and new techniques. I thought long and hard, and the best I could come up is to present this talk online. This is certainly new techniques, and it's very different from the talks at the previous symposium. Nevertheless, I will still try to make the talk somewhat a bit unusual. So I decided to divide talk into two parts. One is to highlight a few latest results, mainly the Higgs physics results, and then some observations of the di-boson and tri-boson process. There are a lot of new LHC results. My apology for the injustice to many other results that I will not be able to show. But please remember to listen to other talks on the LHC results at this symposium. The second part of the talk, we discuss a few results from supposed new ideas and techniques, but probably not particularly new anymore because the results take time to finalize, to analyze. So the techniques also take time to perfect, and it takes time to bring ideas to fruition. And so for the future, what the future physics potential is, please see the talk next by Anadi. I want to mention that actually on my last PHENO conference I attended 10 years ago. I hope the next one is not 10 years later. All right, so here we are. 10 years since the LHC first take data, and we still have a long program to go. Now, LHC has run at 3 different center mass energies, delivered a total about 175 inverse Fendel. And this is only a small fraction of the luminosity envisioned for the whole LHC program. We still have about 95% data yet to come. But you can see here, there's tremendous potential for increasing statistics, but there's very limited potential for increasing center mass energy. So the precision measurement and the studying real processes are likely to be the main physics focus in the years to come. Now, LHC has a very rich physics program, and this project on the right is a bit old, but illustrates the point. And it explores physics over 10 orders of magnitude in rates, and every process counts. From known process, which we use for calibration for precision measurement, to unknown process to test potential new physics. However, there's really 2 types of physics at the LHC. One is the standard model measurement. Other is the search for beyond standard model physics. Now, this plot shows the summary plot from CMS on the standard model cross-section measurements. And what you can see here is, I don't expect you to read from this plot, but the takeaway message is that there are lots of different type of measurements using different type of final states. And there are in general very good agreement between data and theory calculations. And there's unfortunately no confirmed significant deviation from standard model. The other part of the program is search for new physics. Here is an example of mass limit from Atlas on the SUSY searches in different SUSY supersymmetry models in different final states. The mass limit varies, but in general, the limit is around 1 TeV or so. There are lots for other searches, but so far there's no discoveries, and despite the huge amount of effort. Now let me start with Higgs physics by showing you two impressive mass plots. On the left is the 4-lepton mass distribution, showing clearly two resonances. In red is Z to 4 leptons, and in light blue is Higgs to 4 leptons. As you can see here, the background in this channel is very small. On the right is diphoton mass distributions, again from Atlas from the 412 data set. Here in this channel, the continued background is a bit high, but the Higgs resonance on top of continued background is unmistakable. The current status is that the major production process and decay modes have been established, and most of the current analysis now is focused on the precision measurements, studies of production and decay kinematics, Higgs to muon, Higgs to charm couplings, di-Higgs productions, and the search for BSM physics. Now, the bread button physics, Higgs physics, has moved from inclusive measurement to differential and simplified temporary cross-section measurements to enhance the sensitivity to BSM physics. The bottom plot is a comparison of measured Higgs PT distributions from the 4-lepton channel with different theoretical calculations. On the right, on top, the top imaging is an example of so-called simplified template cross-section, which this is called stage 1.2 splitting. Basically, it goes beyond the differential cross-section measurement in slice phase space further. Here you can see the measurement is done in the bins of PT, in bins of number of jets. Bottom plot is such an example from Atlas, and this so-called reduced stage 1.1 measurement, which means you have less spinning, and normalized to standard model cross-section. So vertical line 1 is standard model, and you can see the different measurements are scattered around 1. And despite, in general, they are good agreement, and though the uncertainties are still large. But with more data, of course, this is going to improve. One of the latest results is the Atlas study of Higgs decay to BB. Higgs decay to BB has no leptons or photons in its final states, so you cannot trigger on decay to rely on something else in the event to trigger. Therefore, you study the so-called associated production, where leptonic decays of WZ bosons provide the trigger signal. So in addition to the WZ signatures, you're looking for two B jets that with their mass are consistent with the Higgs mass. And backgrounds are very high, and of course you need we use these BDTs, advanced techniques, to for signal background separation. But I want to show the mass plot actually from the simple cut-based analysis on the right here to illustrate that the huge background. As you can see here, the Higgs signal is very small on top of larger background, mainly top quark and WZ plus jets. On the right is the signal strength measurement. Signal strength is defined as you measure the rate divided by standard model predictions for WH and ZH. The takeaway message here is that we are close to separate observations for WH and the ZH process. And before, of course, we always combine WH, ZH into VH. Another interesting results from both Atlas CMS is the study of the CP structures in Higgs-Top coupling. And as you know, there have been extensive CP studies before, but in the Higgs vector boson couplings, TTH production with Higgs decay to gamma-gamma is ideal for to study the Higgs fermion couplings because the rate is way too high, and the signal can be, Higgs to gamma-gamma can be cleanly reconstructed. So top quark pairs can be easily identified in their leptonic and hadronic decays. if you assume standard model couplings, you can extract the signal strength for TTH, which is CMS measured to be 1.38. That corresponds to 6.6 standard deviation from no TTH production. Now, if you parameterize the coupling in terms of a CP odd and the CP even component, showing here is AHT, then you can CMS using a matrix element-based discriminator to extract a CP odd fraction. The discriminant showing here D. So basically, it's a ratio of the probability for the CP even divided by the total probability, CP even and CP odd. And from that, they set upper limit on the CP odd fraction to be 0.67 at the 95% confidence level. Right is a plot of the discriminant distribution for the data, divided into 3 bins, and also compare with the expectation from pure CP even, CP odd component. Similar results are obtained by Atlas. Atlas also recently released the results on the searches of Higgs decay to Z gamma. In the standard model, Higgs can decay into Z gamma through this loop diagrams, similar to the Higgs decay to gamma gamma. The branching ratio is about 0.15%. Z candidates are identifying their leptonic decays, and therefore, the final state of the lepton plus photon allows for the full Higgs decay reconstruction with good mass resolution. So the search is to look for the bump of a smooth spooling Z gamma mass distributions, as shown on the right. A fit, to the observed data leads to the an observed significance for the Z Higgs decay to Z gamma to be 2.2 sigma with 1.2 sigma expected, which correspond to an upper limit on the signal strength to be 3.6. And this decay mode, I think, will be soon observed, likely in round 3 data. Now, the search for beyond standard model physics in Higgs decay is a major part of the Higgs physics program at the LHC. Here is an example of such search. The Higgs boson could be portal to the hidden sector, which so if so, it can decay into a pair of dark matter particles, lead to invisible or missing energy in the event. Here, Atlas looking for the VVV production of Higgs, followed by its decay, invisible decays. So the signatures to VVV tagging jets recoiling against the missing ET. Multiple control regions and signal regions are used to constrain background to improve signal background separation. Showing on the bottom is the event yields in control region and signal regions. Compare data with expectation. The signal region showing on the right, you can see the dotted line, the dotted red line represents the signals. So from this, an upper limit on the branch ratio for Higgs decay to invisible particle of 13% is set at the 95% confidence level. Now, this limit is significantly tighter than previous results based on the 36 inverse Swindelbaum data set. The improvement mostly come from the, of course, improved statistics as well as analysis technique. Next, I want to talk about quickly the 2 recent observations. One is the observation with Z boson pair production through vector boson scattering. Showing on the left here, your signal is so-called, this from the electroweak diagram. Background, of course, from the QCD diagram. And both the final states studied are 4 lepton channels and the lepton, dilepton, and dineutrino final states. Again, using control regions to constrain background and the BDT for signal background separation. On the right is an example of the BDT distribution from the 4 lepton channels. And you can clearly see the signals in red and the background in blue, clear separation. And So the hypothesis of no electric weak production is excluded at 5.5 sigma. Another is observation of tri-boson production from CMS. And I show a few example diagrams here for tri-W production. You can see this diagram involves cover coupling, linear coupling, and quartet couplings. And they look for same sign dilepton and multi-lepton signature. And on top is the even yield in different electronic final states. Compare data with background expectation. And from combined fit, they derive significance for this production to be 5.7 sigma with these 4 final states combined. And if this table on the left also shows the individual significance for different final states. On the right is the major signal strength. Now, let me switch to the second part of my talk and new techniques and new ideas. So here are a few of my personal observations. The analysis has changed. If you can see, development over the last few, a half decade, there's a wide application of machine learning techniques from searches to triggers. There's a proliferation of signal regions to maximize signal background separations. And we start to explore real standard model process, challenge the theoretical calculation for this process. And another important actual development is the emergence of the really same sign dilepton and multi-lepton final states, and which requires new techniques for suppressing fake lepton contributions. In terms of technical signatures and a field development, the larger radius jets with substructure for highly boosted effective boson and top decays, and techniques for searching long-lived particles, tagging with charm jets, tagging quark jets from ground jets, and so forth. Theoretically, and there are new framework developed to interpret LHC data. For example, effective field theory, simplified template cross-sections, simplified models. And then there's the ideas using high-order corrections to constrain new physics. And of course, there are lots of beyond standard models, new models. And it's not possible for me to cover them all. So in the following slides, I will attempt to sample some of these points. The first topic I want to talk about is tagging with C-quark jets. Tagging C-quark jets is critical for the direct measurement of Higgs charm couplings, which is important for testing your coupling beyond the solar generation. Jet flavor tagging is largely based on the Hadron lifetime, and because they gave a measurable decay distance. For example, proper decay distance for charm is about 100 micron, and for B quark is about 500 micron. And with Lorentz boost, this can be increased by, decay distance can be increased by a factor 10 or more. The bottom left shows the track Desier significance distribution. This is related to lifetime. Compare with B jets in blue, C jets in green, and light jets in brown. Now this log scale plot, you can see C jets tagging with suffer background from both B quark jets and light jets. So it's particularly challenging. On the right is an example of a performance plot for 41% efficiency for C tag efficiency. The rejection for B quark is effect 4, and for rejection for the light quark is effect 20. Now turning to efficiency, that means you have 25% efficiency for B jets, 5% efficiency for light jets, and these are still very high. So one of the application of the critical application is to measure Higgs to CC bar decay. Like the Higgs to BB decays, and we cannot trigger on the decay because then there are no lepton, no the photons. So we rely on social production, so which leads to almost identical final states as Higgs decay to BB. So B jet and C jet tagging the only tools for separating the two. The problem is actually Higgs BB rate is about 20 times higher than Higgs decay to CC. The bottom left is an example plot from CMS, and this look at dye C, after C jet tagging, look at dye C jet mass distribution, and you can see the Higgs to CC contribution can only be visible after significant increase in the rate of the background, C++ background huge. On the right is measure the signal strengths in different analysis channels. And if you look at it, the combined limit is 70 times standard model, the observed one, which is still far away from standard model. Of course, this is based on 36 inverse fundamental. This NAS is complex, so the results of full run 2 data is not yet available. Higgs-Chum coupling can also be determined from the Higgs-PT distribution. Now, this relatively new theoretical development. So, an enhanced Higgs coupling to Chum quark, we modify inclusive Higgs-PT distributions. So, from the measured PT distribution, for example, from Higgs to gamma-gamma decay, Higgs to full lepton decays, we can infer the Higgs to Chum coupling. Left is a theoretical calculation, the modification to the Higgs-PT spectrum for different the coupling modifier. You can see the modification could be large at high PT. On the right is a fit by CMS in the plot showing the contour, the coupling modification to Chum quark on the x-axis, vertical axis, the coupling modifier to B quark. And by fitting to both the rate of modification as well as the shape of the PT distributions, they can constrain the kappa C, which coupling modifier to be ±5. Now, let me switch to Higgs boson self-coupling. Higgs boson self-coupling can be directly probed through the measurement of di-Higgs production, as shown here. And direct measurement based on 36 inverse fundamental has set a constraint on the coupling modifier here. But single Higgs production and decay are also sensitive to the self-coupling through high order corrections. And this, again, another relatively recent development, theoretical development. And these corrections are generally small in standard model, but can be large for larger couplings. Some examples here, showing here, in VH production has high order correction involves self-coupling, TTH as well, and even for the decay, it involves correction with Higgs self-coupling. So large modification can lead to significant changes in the production rates as well as even the kinematics. On the left is examples showing the change to the rates. On the right is change to the Higgs-PT distribution in the ZH production. Use these informations. Atos use both rates and the kinematic information. CMS using the inclusive rates information only. You can set a constraint on self-coupling modifier, as shown here. And these results are competitive with the constraint from direct searches. I'm running short in time, so let me flash very quickly. So one thing actually, search for the using same sign dilepton multi-lepton events has been very productive because it has small rates in standard model, and I expect from many beyond standard physics. Here the example from CMS, they look for same sign dilepton events and to search different supersymmetry models. Example, from Brunel pair production, stop pair production. And another example is using to search full top production, because full top you have full W's in the event, and which can lead to same sign events. And Proton-Proton showing the event yield in 17 BDT beams compared data with background. You can see from the fit, they can extract full top cross section to be about 12 femtobar, and so close to observation. I think it will be also observed in round 3. My next topic, long-lived particles. And particle decays often determine how they are being detected. We often detect prompt decays or decays outside a detector, which can appear as the missing energy or as stable particles. Now, long-lived particle can also decay inside the detector, which leads to displaced vertex, non-prompted jets, etc. The challenge is these events are generally not recorded, and you will need a special triggers and reconstruction software. Here are the 2 examples, one from Atlas, another from CMS. Atlas looking for the long-lived stop pair production. CMS looking for the long-lived Brunel production. One is reconstructed display vertex in Atlas. Another CMS using timing information to separate the signal background. And the bottom prompt is, left prompt is a vertex mass distribution, compare signals with background. On the right is CMS colorimeter timing information. You can see the clear separation between signals and background. Highly boosted object is another interesting development, and this, of course, is not not new, but it has been constant a new development. Recently, CMS published the results using inclusive Higgs to BB decays, and so when PT is very high and Higgs and the 2B just very close, and can be only reconstructed with as a single radius jets. On the bottom shows the mass distribution of the jets. You can see clearly WZ contributions and Higgs contribution shown in pink here is relatively small, illustrate challenges of this analysis. And on the right is they measure the Higgs signal strength for different PD beams, and the uncertainty is large again, but it can improve with data increases. This technique can be also used to search for new physics, as new physics mass scale pushed higher, and there's a larger gap between new physics and the standard model physics, so decay product will be highly boosted. And this feature has been extensively exploited in the search for heavy resonances, particularly in the search for new di-boson and di-top resonance. Showing on the left is an example, these large jet mass distributions from Atlas di-boson resonance search to in the 4 hadronic final states, and you see clearly the effect of boson contributions. On the right is recent results from again from Atlas looking for Z prime decaying to TD bar decaying to 2 large jets. Showing here is sensitivity from the older analysis showing black, and the new analysis showing blue here based on same data set. New analysis using the improved DNN top tag, you can see improvement at high mass with almost order of magnitude. Finally, I want to show one slide on machine learning for particle ID. Machine learning, of course, have prevalent in analysis at the LHC for some time. Now they are being applied to particle IDs as well. Here is the example also called imaging top algorithm from CMS. And using the standard machine, the standard imaging recognition techniques based on neural network, and they pixelize the energy deposit into 37 by 37 pixels, showing on top imaging for top jets, bottom is imaging for light jets, QCD jets, and you can see subtle differences. And based on this, they can achieve 50% tagging efficiency for top jets, while achieve fact 10 rejection for QCD jets. And these techniques paved the way for more innovative analysis. My time is up. Let me conclude by making a few remarks. And there are many new results from LHC. Unfortunately, there's no indication for new physics. And I encourage you to listen to some of the talks at this conference and search for Atlas, CMS website for additional information. LHC will run for next 15 years plus years with 95% of data yet to come, and there's a lot of physics to be done. And see next presentation by Anali. Now with the low-hanging fruit mostly picked, I think now it's more than ever important to for new calculation, new ideas, and new techniques to explore the LHC physics. Thank you for your attention. Stay safe, everyone. Bye-bye.
Thank you, Jianming. That was very nice. If you have any questions at all, right now there are no questions. If you have any, type them into Q&A, and I will read them. I'll give it another minute or two. I was wondering one question that I had, and I'm not sure if it's maybe better for the next talk, but the di-muon decay of the Higgs. I know Atlas has a result that is consistent both with the standard model and with zero. Big error bar still. Can you say anything about the improvements? I mean, are they likely to see it in the next run?
Right now, Atlas, I believe signal strength is like 0.7. So I think to see it, it's a next run is a bit challenge. You need about my the correction, Anadi can correct me, is you need about 500 inverse Fenderbaus to see 3 sigma effect per experiment. Combined, of course, then you can close to 5 sigma. I believe you need a close to 1,000 inverse Fenderbaus.
Okay.
Of course, if we improve mass resolution, now here for this analysis, right, the mass resolution is the key. If we can improve mass resolution, make the peak narrow, and the performance improve. But I think 5 inverse Fenderbaus is needed. Can't estimate.
Okay. We have one question from Chris Krylova. What are some of the other machine learning algorithms that are used?
Oh, there's all kinds of different type of flavor. People, machine learning right now is really, it's wide open. People try to apply different technique. If you look at the current analysis, and most used is VDT is mostly used, and because it's way too easy to use, and neural network used as well to less extent, I think. And then these others, even those have different flavor, right? Machine learning and this imaging technique, again, but that's based on the neural network. There are other, I don't know the really detail. I'm not an expert on this, but even in different BDT neural network, there's different applications and different technique. This parameterized the neural network or a deep learning neural network, a convolutional neural network. There's different flavors. I don't know whether I answer your question, but if you have new ideas, I think people are willing to explore.
Okay, thank you. One other question from Zhen Liu on page 24, the lower left panel.
Yes.
The question is it possible for search for light mass long-lived particles below 10 GeV? Yeah,
actually, well, that's CMS plot. If you look at on the right plot, that's for okay, this is, yeah, oh no, that's also heavy mass. Yes, there's a low mass plot. Okay, I didn't show. Atlas has this neutral LLP, which from Higgs decay. And yeah, you can search for low mass, and the separation, of course, is not as great as high mass, but you can do it, down to like 10 GeV or so.
Okay.
Atlas has results on neutral this LLP from Higgs decay.
Okay, thank you. One more. What is the free path length for STAU if it is a long-lived particle?
Depending on signature use, for Atlas here, Atlas reconstruct the displaced vertex. In that case, basically you need tracks. So you'll talk about C tau, gamma C tau here on the order of centimeter, right? To have tracks. But if you're using colorimeter signature, and then you can, increase to by factor 10 to the meter, or right? Oh no, 100 also to meter, and gamma C tau to about meter or so. And beyond that, of course, you will appeal with decay outside detector, will appeal either as a stable particle, heavy particles, or missing ET.